Okay, so welcome back to the lecture 24 on Riemannian symmetric space. In the last lecture, we have seen this theorem: let M be a Riemannian symmetric space, and let P belongs to M, and G is equal to I M naught, where I M naught is the connected component of identity inside I M. Then we looked at the stabilizer of P inside inside G, and then K is compact, and this G will act as a act smoothly and transitively on M, and this map alpha from G mod K to M given by alpha Gk is equal to G dot P is a diffeomorphism. This is called the orbit map. Okay, so now this map sigma from G to G defined by sigma G is equal to SP. GSP is an involutive morphism of G.
G is the identity component, connected component of the identity of the isometric group, right?
Yes. So the map C sigma from G to G defined by sigma G is equal to SP. SP is an involutive automorphism of G, so that G sigma naught is contained inside K subset of and K is contained inside G sigma, and where G sigma is the set of all fixed points of sigma, and G sigma naught is the connected component of identity in G sigma. So also we have I have also used this theorem, which I am writing it once more because I am going to use this thing. Let G be a Lie group and H be a closed subgroup of G, then G by H is a smooth manifold. Okay, we have seen that. Then G by H, G mod H equipped with quotient topology has a unique smooth structure on it with the property that G is a transitively transformational group of the manifold G mod H. Okay. So this much this proposition I will use now. Listen. So now I want to give some discussions. Let G and H be two Lie group, and let phi from G to H be a Lie group homomorphism. That means this is a smooth map and this is a group homomorphism. So Lie group homomorphism. Okay. And then this kernel of phi, this is a closed normal subgroup of G. Now this Cartan's theory, Cartan's theorem says that if G is a Lie group, any closed subgroup of that G is also a Lie group. So therefore, hence by this Cartan's theorem, this kernel of phi is a closed normal Lie subgroup of G. Of G with Lie algebra. Actually, what will be Lie algebra? If you can guess that, this will be Lie algebra is kernel of T phi. Lie algebra is the kernel of T. So one can prove that, and I'm leaving that proof for you, and you can take it an exercise. You have to use this commutative diagram, this which I have showed that from phi is a map from G to H. G to H. This there is something called exponential map here, and this from G to H, the D phi. Okay, so kernel of phi is a closed normal Lie subgroup of G with Lie algebra. Okay, so and what is with Lie algebra? What is Lie algebra? This is kernel of D phi. You have to use this commutative diagram, and this diagram is really extremely important. Okay, now from
you don't need to assume these are connected Lie groups, right?
No,
that doesn't matter, right?
No, here it does not matter. Connectedness, I will see something. Okay, so from this third isomorphism theorem, okay, so we have this thing, this G mod kernel of phi. This is really isomorphic to phi of G. So this is just a abstract group of homomorphism.
Munna, is according to your notation, d phi means d phi at E.
Yes, sir. Yes, sir. D phi means D phi at T. So G mod kernel of phi is a really this is from third theorem of group isomorphism. This is uh, sorry. G mod kernel of phi is isomorphic to phi Z. This is I should write this abstract group isomorphism. Okay. Now the thing is, kernel of phi is a closed subgroup of G, and therefore G mod kernel of phi has a smooth manifold structure. Okay. And another thing is the kernel of phi is also a normal Lie subgroup of normal kernel of phi is normal of G, normal in G. So this mod kernel of phi is a group. Okay. And so it has a smooth manifold structure and it has also group structure. So one can show that group operations are smooth with respect to that smooth manifold structure. Okay. Therefore, G mod kernel of phi is a Lie group. Okay. Is a Lie group. Now, what you do that you use this isomorphism to give a smooth structure on pi G. Okay. So we borrow the topology and smooth structure. We have to borrow is topology also. Topology and smooth structure of G mod kernel of phi to phi Z. Now this phi Z becomes a Lie group. Okay. And it becomes a submanifold of H. So this phi Z, yes, phi Z becomes a Lie subgroup of H with Lie algebra. You can also sort of guess what will be Lie algebra. This will be d phi G. And what is d phi G? This is really d phi x, so that x belongs to G. So you can use that diagram also prove this thing. So I am leaving this proof. Okay, so you can take it an exercise, if you, or you can look at any Lie theory book. For instance, Helgason, you will get this. Okay, so and another thing, remark. This topology of phi Z is not really coming from the H. Okay, it is just a submanifold. So we have to write this thing. So it may not be true that. So it topology of phi Z may not really coincide with subspace topology of topology of H. Can have subset topology of no subset topology coming from H. Okay. But if it happens that G is compact or G mod kernel of phi is compact, then phi G will have the subset topology because of this theorem that X is compact and Y is half-top. If F is continuous and 1 1 and on 2, then F is an open map. For that reason, that if G is compact or G mod kernel of phi is compact, then IG will have necessarily the substrate topology of H. Okay, so this is the thing we want to apply this whole formalism to a particular case, that is to our adjoint representation. So one application is something. So we know that this adjoint map from G to GLG is a smooth group homomorphism. homomorphism. Now the thing is, let H be a subgroup of G. Least be a least subgroup of G. So then I can restrict this adjoint to the H, and that will also become a smooth map. But since here two groups are there, so let us write this as RG. Okay, that means this is adjoint representation of G. So thus RG from H to GLG is also a smooth representation, also a smooth group homomorphism, Lie group homomorphism. Now, by previous discussion, this RGH, okay, is a Lie subgroup of GLG. Subgroup of GLG with Lie algebra. See, the thing is, okay, here what was the Lie algebra? This is d phi, where phi is the derivative of phi at the identity, and derivative of capital R is small r. So with Lie algebra, small r, G, and H. Okay, okay, so where H is the Lie algebra of H. Okay, I am writing here. Let H be a Lie subgroup of G with Lie algebra H. Okay, so this is the RGH is a Lie subgroup of GLG with Lie algebra RGH. So as I have remarked here, this topology. Topology of topology of RGH may not coincide with the subspace topology. May not coincide with the subspace topology from GLG, coming from GLG. Okay, so now this is the preparation which I needed. Now I want to define something called Riemannian symmetric pair, and this is a very important concept. And so Riemannian and symmetric pair, and I will use this abbreviation RSP. RSP stands for Riemannian symmetric pair. So definition. So let G be a connected Lie group. Here I am assuming this connected. And H be a closed subgroup of G. Okay. The pair G comma H is said to be a Riemannian symmetric pair. So let me write this faster. Riemannian symmetric pair, and I will use this abbreviation RSP if it satisfies these two conditions. If first condition is there exists an involutive automorphism sigma from G to G, so that this H will be sandwiched with in between this G sigma and G sigma naught, okay, where as usual this G sigma is the set of all fixed points of sigma. X belongs to G, so that sigma x is equal to x, and this G sigma naught is the connected component of identity. Component of identity in G sigma. Second thing is I have to add this condition RGH is compact. Okay, so let us quickly see the definition. Let once more. Let G be a connected Lie group and H be a closed subgroup G. The pair G, H is said to be a Riemannian symmetric pair RSP if there exists an involutive automorphism sigma from G to G, so that G sigma naught is contained inside H and H is contained inside G sigma, where G sigma is equal to X belongs set of all fixed point of sigma, and G sigma naught is the connected component of identity in G sigma. And second thing is RGH is compact. So remark. So since this RGH is compact, so in this particular case, this RGH will have the matrix topology. So remark, since okay, if GH is a RSP, then RGH is really will have the subspace topology. Topology and coming from this GLG. And what is the reason? This because RGH is compact. And reason
That means you need only to be closed, right?
which
At GH is closed, so that's why it has the subspace topology, right?
yes, closed and yeah, closeness is enough, but the thing is, okay, since you are getting this RGH is compact, therefore this is, so this RGH is compact. But that is a non-trivial theorem.
Which one?
Anyway, this closeness.
Yeah.
Anyway, so that is a different thing. So now one example.
So why is it called Riemannian symmetric pair?
Riemannian symmetric pair.
Yeah.
Because
How are you getting
because
symmetric space?
you will get symmetric space. It will take 4 or 5 lectures to really prove. This is the
Okay.
actually theoretic characterization of means symmetric space. Okay. So it will take 4 or 5 lectures to really establish that. This is not a small. So example. So let M be a RSS and P belongs to let P belongs to M. G is equal to I am naught, and this K is equal to really stabilizer of G inside P. Since K is compact, so this implies clearly this RGK is compact. So second condition is satisfied. So let sigma from G to G be given by this. So sigma G is really SPZ. SP, we have already seen that. We have seen that this thing that G sigma naught is really okay. Sigma is an involution, and this sigma naught is really K is this subset of G sigma, and this is an involution. Okay, and so I am not writing. Okay, sigma is an involution. This is an involution. Okay. Therefore, this GK is a Riemannian symmetric pair. So Therefore, this GK is a Riemannian symmetric sphere. Now the thing is, and this example actually this.
So if you just out of curiosity, so if you have a Riemannian symmetric pair G comma H, so what is the symmetric space G mod H?
Yes, G mod H. So in fact, this example serves as the motivation for this definition, this of Riemannian symmetric sphere. But there is only one condition which might be, which might appear to you, all of you strange. This RGH, why I am taking this RGH is compact, and we will see why this condition is coming. This is exactly the condition which is needed to make this G by S a Riemannian manifold. Okay, we will see this thing. Okay, so this
Compactness will give you that bi-invariant metric, right? Is it?
compact? No. So we will see
Because
that why so RGH is compact will give something. Okay, not by invariant, G invariant metric on G mod S.
okay.
Who is acting from both sides on G mod H? Nobody is acting from both sides. G is acting from the left.
Yes, only
Why
left
that
invariant.
doesn't make sense?
Yes, sir. By invariant will not make sense here. So therefore GK is a Riemannian symmetric pair. So now some discussion. Okay, so let G comma H be a Riemannian symmetric pair with associated involution sigma. There is an involution in the definition, sigma from G to G. Okay. So okay, I just wanted to uh, prove some small proposition before that. Then we will go to the discussion. So proposition. So let sigma from G to G be as a Lie group homomorphism. Okay. So I will not write the conclusion. I will just start the proof. Then after that I will write the conclusion. Okay. So let's see. So if you let this sigma composition IGH, so this is a sigma of the sigma composition IGH. Okay. So IG is the conjugation by G. This is sigma G.
Una, I'm sorry, I just got disconnected in between. Can you please scroll up? I missed something. No. Therefore, GK is a Riemannian symmetric sphere. So you started with the manifold and got G and K, is it? You didn't start with G. This part I missed. You had
No. Yeah, this
got
is
a
the
G
part
out
of this
of that.
example.
Okay.
That this is
Fine, thank you.
this is the part of the example.
Yeah, fine, thank you. I'm getting disconnected in between.
Okay, so now it is okay. So after that, therefore GK is a Riemannian symmetric pair where G is really I am not. Okay. So now what I state that I will prove a proposition. Okay. So let sigma from G to G be a Lie group homomorphism. Okay. And I am not writing the conclusion. I will write that later because I cannot remember the thing. So sigma of IGS is equal to really sigma a GH G inverse. Since sigma is a group homomorphism, I will get sigma G, sigma H, sigma G inverse. Okay. So this is same thing as I of sigma G composition. Okay, I of sigma G applied on sigma H. And this is really I sigma G composition sigma applied on H. So I will get that sigma composition IC is equal to I sigma G composition sigma. Okay. Now I can take the derivative at the point identity. So d sigma diz e. So di sigma G is composition d sigma Okay, and I will evaluate everything at identity. So d sigma E is our d sigma. Okay, so this is by notation. D of Ig is really Rg, and this is really R of sigma G, and this is really d sigma, composition d sigma, and this is my conclusion. So then uh, R of d sigma composition Rg really is equal to your R sigma, R of sigma G composition d sigma. And this happens for all G belongs to it. So d sigma composition Rg equal to R sigma G, R sigma G composition d sigma, and this happens for all G. Okay, we will remember this proposition. We will use this thing. Okay, now I will go to the discussion. So let G comma H be a Riemannian symmetric pair with with associated involution sigma. Sigma from G to Z. Now this is the sigma square is equal to really identity because sigma is an involution. Now if I take this thing derivative of the point identity, derivative of this, I will get d sigma e square is equal to identity. And d sigma e square, d sigma e, actually I denote it by d sigma, right? So this is d sigma square is really identity. And d sigma is a Lie algebra homomorphism. And d sigma is an invertible map here. So d sigma is really uh, d sigma is a Lie algebra automorphism. Lie algebra automorphism of G. Now the thing is d sigma square is identity. So this implies so okay, so really. So eigenvalues of d sigma are really plus minus 1. Plus 1 or and minus 1. So let k. So, this k is the plus 1 eigenspace of d sigma. This is x belongs to G. So that d sigma x is equal to really x. And this, okay, and this is P. P is equal to really x belongs to G. So that d sigma x is equal to minus x. So this is the plus 1 eigenspace. And this is really minus 1 eigenspace. So now thus we will get what? This we will get this thing that G is equal to really K plus P. And this sum is really direct sum. This is really direct sum. Okay. Now, if x belongs to G, then you can write this thing as x. This is the decomposition. You can write this x as x plus d sigma x by 2 plus x minus d sigma x by 2. And this you can write this as uniquely. Okay? And this fact this x plus d sigma x by 2, this will belong to K and this will belong to P. Now suppose okay, so we have get this decomposition. This decomposition will be called Cartan decomposition. So we have written this G is equal to K plus P. Okay. Now we have this automorphism sigma. Okay, and so let x belongs to uh, let let x belongs to Lie algebra of G sigma. So remember what is G sigma? This G sigma is the set of all fixed points of sigma. This is equivalent to this fact that x belongs to Lie algebra of G sigma. This implies exponential of Tx belongs to G sigma for all t belongs to R. Okay. Now that will give you that sigma, and this is equivalent to the fact that sigma of exponential of Tx is equal to exponential of Tx. This for all t belongs to R. Okay. Now sigma of exponential of Tx, this is really exponential of T of d sigma x. Okay. And this comes from that commutative diagram which I really told you. This is equal to exponential of Tx for all t belongs to R. Now the thing is, if you take the differentiation with respect to t and put t is equal to 0, then you will get what? D sigma x is equal to x. So differentiating with respect to t and at t is equal to 0. So this will, you will get this thing that d sigma x is equal to x. That means x belongs to the plus one eigenspace of d sigma, and this is really, the thing is, x belongs to k. So you have started with x belongs to Lie algebra of G sigma, and you are getting that x belongs to k. So this implies, thus we get so Lie algebra of G sigma is really okay. Now okay, since this is a Riemannian symmetric, we also know that this the G sigma naught is contained inside A. This is contained inside G sigma, and therefore Lie algebra of G sigma naught is really contained inside Lie algebra of H and Lie algebra of G sigma, and these two things are same. Why? Because I have told you sometimes that if suppose G is a Lie group and G naught is the connected component of identity inside G, okay, so then Lie algebra of G and the Lie algebra of G naught is same. So I am applying that thing. Okay. So thus we get, so Lie algebra of H is equal to Lie algebra of G sigma naught. This is equal to Lie algebra of G sigma, and the Lie algebra of G sigma is equal to really what? K, right? Now, okay. Now I want to, our claim is really.
Mona, just a minute. I again missed something.
Yes, sir.
Lie algebra of G sigma naught is contained in K that you have shown.
No, I have, sir, I have shown the Lie algebra G sigma is equal to K.
How does this equality follow? If
For,
and only we can go the reverse way. Okay.
yeah, actually, if and only if I have put it here also. So, yes, x belongs to K, that implies D sigma x is equal to x. Okay. So forget about this line. You just see, sir. You'll get it. Is it okay, sir?
See K.
Don't wait for me. Proceed.
Yeah. So here actually we also know that G sigma naught is contained inside H, and that is subset of G sigma. So this line is trivial. Lie algebra of G sigma naught is equal to subset of Lie algebra of H and subset of Lie algebra G sigma. Since Lie algebra of a group and its connected component are same, so these two things are same. Lie algebra of G sigma naught is equal to Lie algebra of G sigma. So therefore, I will get Lie algebra of H is equal to Lie algebra of G sigma naught is equal to Lie algebra of G sigma. This is equal to K. So claim this is P not equal to 0. Now to show that, suppose P is equal to 0, that this will imply that K is really will be G. So therefore, both G sigma naught and G are connected. B subgroup of G which has which have same Lie algebra. And I have told you that if G is a Lie group, this theorem actually I have stated somewhere. If G is a Lie group and two connected Lie subgroups have same Lie algebra, then they have to same. Okay. So I have stated that thing in some theorem. So therefore,
You assume G is connected.
yeah, because that is a part of the definition that Riemannian symmetric pair.
Okay.
Therefore, G is equal to really G sigma naught. Okay. If you do not want to use this theorem, simply use this fact that exponential generates the exponential of a neighborhood of a, on the Lie algebra generates the connected component. If you will not, so but G sigma naught is contained inside G sigma. So thus we will get that G is equal to G sigma. That will precisely means that sigma is equal to identity. Means okay. So what is the meaning of the statement G is equal to G sigma? That means that sigma all the points of G are fixed points of sigma. Therefore, so this implies that that sigma is equal to identity and sigma is an involution, which is a contradiction. So, so P is not equal to 0. So that means here look at this thing. D sigma P is not equal to 0. So that means D sigma is not identity. And D sigma square is equal to identity. So therefore, thus we get that thus D sigma is an involutive automorphism of C. Okay. So it is also clear that also easy to see that. See this, if you look at this K Lie bracket of K and K, this is a Lie algebra. So this is really contained inside K. And this KP, okay, this is contained inside P because D sigma is an involutive automorphism of G, and this is really belongs to the +1 eigenspace, and P belongs to the -1 eigenspace, and this +1 and -1 eigenspace, Lie bracket of that will be inside the -1 eigenspace. Uh, similarly this P. Okay.
Just a second. So K is a Lie algebra. So K bracket K is contained in K, right?
Okay, that's yeah. You can argue this way, or in this way also you can argue.
But no, but why is K comma that whatever is your
P,
notation that is contained that?
because D sigma is an involutive automorphism, and K belongs to K is the +1 eigenspace, and P is the -1 eigenspace. So Lie bracket of +-1
So
is
that will
called.
multiply. Eigen value
Okay,
will multiply.
I will do it. I will do it. But if you are not really okay, so let us see. Let us understand. Okay, let me say this, and then I will show them. So P is contained in the -1 eigenspace for D sigma and -1 eigenspace. This will contain inside +1. So let me prove this second one. Okay, this everything will be.
Mona, you mean
Yes.
PP subset of K?
Yes, sir. Yes, sir. Yeah. Thanks. Sir. So proof of the fact is actually this KP. So to show that, let X belongs to K, Y belongs to P. Then this D sigma really XY. So D sigma is a Lie algebra automorphism. So that will be d sigma x and d sigma y. Since x belongs to K, so d sigma x is equal to x because this is the plus one eigensphere, and d sigma y is equal to minus y. So this is Lie bracket of minus of xy. Thus, this xy belongs to minus one eigenspace of d sigma, and this is the definition of P. So hence we get this thing. Kp is Manoj, is this clear?
Yes, yes. Thank you.
Similarly, you can really prove this thing. Okay, so this is the thing I have shown that now. Now I want to make an important claim. So this is really so RGHP is really contained inside P. So what does that mean? This, if you look at the action of RGH on P, that means P is invariant under the action of RGH. Okay. So let me let us prove that. So let H belongs to H. Okay. So I have to realize what I have to show that, and let H belongs to H and X belongs to P. So we need to show that RGH applied on X, this belongs to P. Okay. For that, actually, I have to really apply d sigma on this thing, and if it is let us apply that d sigma on it, then what we get, let us understand. So this is really d sigma composition RGH X. Now you really apply that previous proposition which I have proved for you. D sigma composition RGH is really RG sigma H composition D sigma. Yes, actually I have proved this proposition. I think, yeah, this was the proposition. D sigma composition RG is really R sigma G composition D sigma. I am applying that thing. So let us write this thing by a previous proposition. Okay, but since but sigma H is equal to H. Okay. Since this because H is contains inside G sigma, therefore sigma H is equal to H. So I can write that RG sigma H is equal to H composition D sigma S. Okay. Now I can open the bracket. So RGH is composition RJ applied on D sigma X. D sigma X is equal to minus X, right? So minus X, because X belongs to P you have taken. So this is really minus of RGHX. Okay. Thus we get this thing that RGHX, this belongs to P. Hence the claim. Hence we have proved the claim. So let us write everything in terms of the theorem. So thus by preceding discussion, we get the following theorem. So let us write that theorem. This is an important theorem, and so let GH be a Riemannian symmetric pair associated with the involution with associated involution. Let us say involution sigma from G to G. Okay. Then this theta theta is equal to d sigma is an involutive automorphism of G, automorphism of the Lie algebra. And this involution is called Cartan involution. Cartan involution. Okay. So let this k is equal to what? This was the plus one eigenspace of theta. Let k is equal to x belongs to G, so that theta x is equal to x, and p is equal to really x belongs to G, so that theta x is equal to minus x. So then this G is equal to direct sum of k plus p, and this decomposition is called Cartan decomposition. This is called Cartan decomposition. Okay. And this is not, this is a direct sum. Okay. With really p is equal to not equal to 0. Actually, this thing theta is an involution automatically implies that p is not equal to 0, but I am writing it because so there is some redundancy in the thing. Yeah, somebody else is saying something. Moreover, we have this thing. Kk is contained inside. So writing this Gothic letter is Kk is contained inside K. This Kp is really contained inside P, and this Pp is really contained inside K, and this thing RG SP is really contained inside P. So this is the theorem. Actually, we have really proved. So I will refer to this theorem by Cartan decomposition theorem whenever I will need this thing. So the theorem is let G, H be a Riemannian symmetric pair with associated involution sigma from G to G. Then this theta derivative of this sigma identity is an involutive automorphism G, and this is called Cartan involution. And let is k is the plus one eigenspace of theta, and p is the minus one eigenspace of theta. Then G is equal to k plus p. Then moreover, we have this thing k leave bracket of k and k is contained inside k, and leave bracket of k and p is contained inside p, and leave bracket of p and p is contained inside k, and this thing RGS p is okay. As I said that there is some redundancy in this statement because p not equal to 0 will imply from that the fact that theta is an involution, and there is also some other redundancy. For instance, this condition RGHP subset of P will imply this condition, this KP, curly bracket of KP is subset of P. Let me write that remark. So if G and H are as in the previous theorem, then this RG HP P, the condition this will imply that this K P is really this is contained inside P. And now what is the proof? Proof is very simple. Proof is if let okay, so let RGH P is really subset of P, and let X belongs to K, and this Y belongs to really P. Then if X belongs to K, this will imply this exponential of Tx. This belongs to H because H is because K is the Lie algebra of H, and I have really okay. Actually, I have to add one thing here. Actually, P is equal to 0, and actually, sorry, I missed something here, and this Lie algebra of H is equal to K. You have to add this condition. So since x belongs to the Lie algebra of H, so exponential of Tx belongs to H, or all T belongs to R. So that means RG exponential of Tx y, this will belong to P, or all T belongs to R. Now R of G of exponential of Tx, this is really e to the power T RG x. Okay. This thing is really this thing. Okay. This. So this y belongs to P for all T belongs to R. Now if you take this differentiation with respect to T at T is equal to 0, so differentiating with respect to T at T is equal to 0, we get this thing that RGXY, this is really XY, Lie bracket of XY, this belongs to P. So hence the hence the proof. So RGHP is subset of P will imply that Lie bracket of K and P is contained inside P. Converse implication is always not true, but it is true only when H is connected. Okay. So converse implication is also true when H is connected. Proof, let us say, suppose H is connected. And this thing that and Kp is really contained inside P. So this implies, so let x belongs to K and y belongs to P. Now what is this e to the power rx rgx y? This is simply that this thing is rg x to the power n by n factorial, n is equal to 0 to 1 y, and this condition K, okay, this Lie bracket of Kp subset of P, this will imply that Rg x y belongs to really P, and this happens for any x and y. Okay, if you use this fact repeatedly, this Rgx y belongs to P, and this happens for any x and y, so that will show that this will belongs to P. So this will imply that, and what is e to the power Rgxy? This implies this is really R. This is really R of exponential of x. Okay, just wait 1 second. Yeah, this one. So this is really Rg exponential of y belongs to P for any x comma y belongs to P. Okay. So this is the thing. Now as h, now let h belongs to h. Now as h is connected, this will be generated by exponential of a neighborhood in the Lie algebra. As h is connected.
Isn't x in K?
Yes, sir. X is K. Oh, yeah. For any x, thank you, sir. For any x belongs to K and y belongs to P. Sorry, thank you. As H is connected, this implies H is equal to really something like exponential of x1, exponential of x2, and exponential of xk. H can be written as like this for some k belongs to n. Okay, let us not write k here. Write n for some m belongs to n. So this is will imply that RGH. Really, since R is a group homomorphism, this will be RG exponential of x1 and RG exponential of x2, and this is really RG exponential of xn. So now if y belongs to P, y belongs to P, RGHY, and this is same thing as RG exponential of x1, so RG exponential of x2 and RG exponential of xn y. And we have shown that RG exponential of xy belongs to P for any x belongs to K and y belongs to P. So that will imply that this will belongs to P. And if you use this fact, because here x and y are arbitrary, so if you use this fact repeatedly, so then you can conclude that RGHY is belongs to P. Okay. So let us call this as okay. So thus thus we get that RGH y belongs to P. Hence RGH is really contingent. So there are some redundancy, but if H is connected, then these two conditions, okay, the K Lie bracket of K and P is contains at P, and this fourth condition they are really same. But I want to go but in the Riemannian symmetric pair, H may not be connected. Only we are trying the condition that G is connected. So these conditions are not really equivalent. But we will write everywhere this four condition because these conditions will use frequently. So these are sort of handy. This will be sort of handy. Okay, so now okay, so this is the thing. Now actually I just want to say one thing that in this Cartan decomposition theorem, we are saying that P is not equal to 0, but it may happen that K might be 0, okay, but P is non-zero. So let me give one example for that. Okay, we will actually produce a lot of example of Riemannian symmetric pair, and this is the probably the uh, main recipe to produce examples of symmetric space, Riemannian symmetric space. So okay, so I will just give one example where this K is equal to 0. Okay. So example, so let okay, let us see first. Let G is equal to really S1, your unit circle, and sigma from G to G is given by sigma of Z is equal to Z inverse. Now Z belongs to G sigma. This is if and only if sigma Z is equal to Z, and if and only if this Z inverse is equal to Z. This is if and only if Z square is equal to 1 and Z is equal to plus minus 1. Okay. So here actually G sigma will what? Here this sigma is equal to 1 minus 1, and or G sigma is not and okay, not or this is and this thing G sigma not is equal to really 1. Okay. Now so if you take this clearly this G sigma and G sigma naught is equal to R compact and discrete also. So if I take this so that means Lie algebra of G sigma is equal to Lie algebra G sigma naught. This is really is equal to 0. If you take this, if we take H is equal to either this G sigma or G sigma naught. So clearly this this GH is a Riemannian symmetric pair with uh, K, which is the Lie algebra of H. This is equal to 0. Similarly, you can construct this example for any uh, connected abelian Lie group. For instance, you can also take this thing, let G is equal to Rn, and you can define sigma from Rn to Rn by sigma of Z is equal to minus Z. Then G sigma is equal to really 0, and this okay, so G sigma is equal to 0, and then this thing actually Rn and 0 is a Riemannian symmetric pair with this K is equal to Lie algebra of H is equal to with K is equal to 0. Okay, so this is there is nothing great about it, and you can also modify this example that where you can take this G as a connected abelian Lie group, and the involution in that case you have to take this sigma G is equal to G inverse. If you take that, then you can construct more examples. But okay, so we will come back to this thing later. Okay, so now the thing is okay, so actually our what is our goal for next 2-3 lectures? We will prove that if you give if there is a Riemannian symmetric space, you can really you can construct a Riemannian symmetric space out of it. Okay, so if suppose G mod H GH is a Riemannian symmetric pair, okay, then what we will show that first we will say that M is equal to G mod H is a Riemannian manifold. Then you can we will show that this G mod H is a Riemannian symmetric space. Okay, so now first we will consider this aspect. This when so whether G mod H is a Riemannian, how to show that this G mod H is a Riemannian manifold. After that we will then show that how we can after that we will see how we can make this M is a Riemannian symmetric space. Okay, to show that actually we have to really do some work, and we are doing some work. Okay. So now I want to really little digression, so proposition. Uh, so we need to okay some. So let K B be a vector space over field K, where this K is equal to either R or C. Okay. So let A comma B belongs to endomorphism of uh, K over B, so that this AB is equal to BA, so that A and B commutes. So then A preserves the preserves the image of B, preserves image of B. Okay. What I write? Image of B, null space of B, and eigenspace of B. And eigenspace of B. This is a very simple proposition, and also easy to prove. You can prove it. I will leave this for exercise. This is a very, probably you have seen this thing. So this is a very simple looking proposition. It says that if A and B are two linear operator which commutes with each other, A preserves image of B, null space of B, and eigenspace of B. This is a very simple looking proposition, but this is a very powerful proposition. Okay, in my opinion, if you want to study this Peter-Weyl theory or representation theory, there are two simple tools to study that representation theory. This is one. This proposition is one, and another thing is every compact self-adjoint operator is diagonalizable. And this proposition is very dear to me, and hopefully we will explore this proposition later. Okay, so now, okay, so now I want to really see another proposition. So let G be a group which acts irreducibly on a real vector space B. Okay, so let this thing be a G invariant inner product on B, and let B be a simple B be a symmetric bilinear form on B. Then there exists lambda belongs to R, so that this B of UV is equal to something like lambda UV. This is for all UV belongs to. So let G be a group which acts irreducibly on a real vector space B. Let this be a G invariant inner product on B. Let B be a symmetric bilinear form on B. Then there exists a lambda belongs to R, so that this thing B of UV is equal to lambda of UV. Okay, so I missed something. Let B be a G invariant symmetric bilinear form. Sorry. Okay, so in particular this in particular there exists a unique G invariant inner product. Okay, G inner product on B up to scalar multiple. Okay, so this proof is very simple. Probably most of you have seen this thing. Let me just keep that. See, the thing is here there is one subtlety. This complex, this field, scalar field is not really complex number. This is a real number. This is the only subtlety. Okay. So proof. Okay, so as this B is a symmetric bilinear form on B, by Rie's representation theorem, there exists L belonging to this linear L in a linear map. There is a linear map L, so that B of UV is really LU. Okay. So since B is a bilinear form on B, so by Rie's representation theorem, there will exist some linear map L So that B of UV is equal to inner product of LU comma V. Okay. Now as B is symmetric, this B of UV is equal to B of VU. This is really LUV, inner product LVU. And this LVU, you can write that is really V L transpose U. And this is same thing as L transpose U inner product B. So this implies L, and this happens for all U V belongs to B. That this is really L is equal to L transpose. This means L is symmetric. So and therefore is since L is symmetric, therefore L has a real eigenvalue lambda. Real eigenvalue lambda. Lambda is real. So let n lambda is really kernel of L minus lambda I, and this is non-zero because lambda is an eigenvalue simply. So now claim this G commutes with L action. So claim G dot L is equal to really L dot G. So to show that we need to prove that GLU G. This is really common. This is really LU G inverse P. So this is same thing as really B of U. Okay, so G dot LU inner product B is equal to LU G inverse B. I am using this inner product which is G invariant. Since this is really G invariant, I am using it. So this is same thing as B of U G inverse B. Now you am using that B is also G invariant. So B of this is G U and this is B. Okay. So but this is B of G U is really this is L of G U B. G invariant. So from this thing, and this happens for all UV block V. From this thing, you are getting that G dot L is equal to L dot G. So hence we get. So G dot L is equal to L dot G for all G belongs to G. Now since this G commutes with L, action of G commutes with L, and I have told you that if two linear operator commutes with each other, then that will preserve the null eigenspace of the other. This implies G of n lambda is subset of n lambda for all G belongs to G. So this implies n lambda is a G invariant subspace of B, and since n lambda is not equal to 0 and B is irreducible, so therefore this n lambda is equal to B. Thus I will get that, thus we get this L is equal to really lambda I. Hence B of UV, this is really LUV, this is really lambda of UV. So for all UV belongs to B. So hence this is the hence the proposition I have proved. So now it may not happen that if G is any group. So actually I have assumed one more assumption on a finite dimensional real. Sorry. Actually I should have on a finite dimensional real in product space. Okay, so if if G is any group, it may not be really possible that and suppose G acts on B, it may not be always possible that this you will get an G invariant inner product on B. So what I am saying, I am saying is suppose G acts on B, it may not be always possible that you will get a G invariant inner product on B. Because for instance, G is a group like SL2R or something, so you cannot really probably you may not get a G invariant inner product on B. And another thing is, it is also not necessary that this if G acts on irreducibly on a space B, the dimension of B is finite. It may not be always possible, but if G is compact, there is a standard averaging technique which I have told you also. Then you will get a G invariant inner product on this way. So let me write that corollary remark just. So okay, I will take a 5 minute more so that we'll start a next. I will start a new thing in the letter. We will complete this proposition. So let G be a compact group which acting on a real vector space, okay, atomic vector space over K, where K is equal to either R or C. Then there is just a G invariant inner product. As a proof is clear that you use that the standard averaging technique. So let this be any G invariant inner product on P. So define this thing. Define a new inner product UV. This is really GU GV DZ, where this is the DZ is the normalized R measure of G. Then this new inner product is, then this is a G invariant. So this is a very simple thing. So that thing, and let us give one application, this which I will use that thing. So application. So since okay, so you know that this group SON acts transitively on Sn-1. So using this fact, it is not really difficult to see that action of SON on Rn is really reducible. On Rn is reducible. So then by previous proposition, then by one of our previous proposition, this there exists a unique SON invariant inner product on Rn. Now you know that the usual L2 inner product on Rn is really SON invariant, since usual L2 inner product on Rn is SON invariant. So any SON invariant the inner product on Rn will be a scalar multiple of usual in L2 inner product. Multiple of usual L2 inner product. Okay, so this is really this is a very interesting corollary, okay, of this thing, this which we have proved, and we will use these facts in later, and we will see what are the implication of these things. And in the next lecture, we'll start talking about something called isotropic representation, and we will talk about. We will see that how G mod H can be made a Riemannian manifold. We will really go into this Lie theoretic characterization of Riemannian symmetric space. It will occupy at least 5-6 lecture. So with this, I would like to stop. Okay, I will be happy to answer any question if there is any. Tapendu, is this thing clear? Anway, Tapendu.
Yes, ma'am. Except in the last proposition, could you move to the last proposition? So it's the application, it's the proposition of.
Okay, this is not the.
So in the proof you started with let G inner product.
Oh, sorry.
Yes, no, right?
Okay, it was really since I was in a hurry, therefore.
Any
Any inner product.
Okay.
Any invariant. That's it. And this thing is this. Is this the fact is clear? SON acts transitively on Sn minus 1, then the action of SON is on Rn is irreducible. Yeah. Tapendu,
No.
this is clear, right?
Not for me. I don't recall.
What you are saying?
I don't know. Means I'm not sure. There was some argument used in IM that.
No.
From there
See, the thing is, so you take. So what I'm saying that. So okay. So what I am saying that action of SON on Rn is irreducible. I have to prove that, right? So let W be any SON. Okay, let's SON invariant. This non-zero subspace of you should have asked this thing, subspace of Rn. Okay.
Yes.
So since this is non-zero, so there exists some W belongs to Sn minus 1, and okay, so there exists some W belongs to W with this norm of W is equal to 1, because you can scale it, because since W non-zero, so there will exist some non-zero W, and you can scale it. That vector will be belongs to W.
Yes. Yeah.
Okay. Now since SON, okay, if you look at this action of SON in W, okay, that said would be lie inside W, because W is SON invariant.
Yes.
Yes, but SON W is whole. What is this thing? This is whole Sn minus 1.
Yeah.
And this is whole Sn minus 1 is contained inside W.
Yes.
Now, if whole Sn minus 1 is contained in W, therefore this will imply that Rn is subset of W, because you can scale it, because that is a vector space.
Yeah.
So you are getting that W is equal to Rn.
Okay.
This is the thing. Okay. Is there any question? Any other question?
No. That was.
Okay. So Pritam, will you stop?
Pritam has from internet column he messaged me. He asked me if any concern is there.
Yeah.
Python was having internet connection. Manava.
Okay. So I think I should stop then.
Yeah. The recording will automatically stop.
I don't know. Okay.